In this video, we're going to look at an application of the binomial distribution. But before we get to that, I wanted to say just a few things. I think it comes through in these videos that I, in general, have a very high opinion of the textbook that we're using. I think that the writer, Michael Sullivan, did a really nice job, and this is a really excellent text for this course. But that doesn't mean that I agree with everything in the book or that I would teach everything the way it's found in the book. And so the section covering the binomial distribution is one of those sections. You might get a very, well, I don't know, not a good idea of how to do these binomial problems if you're following everything you see in the text here. And so this is a great example that you can see on the screen here for explaining why we have what we have for the various values. And there's a lot of good detail here. But you'd be mistaken if you thought that this is the way we always calculate binomial probabilities. And so that's part of what we wanted to address in this video is what we do in terms of calculating these binomial probabilities. Let's take a look at something here. Now, we make heavy use of the calculator when we do binomial applications. And so for that reason, the lens through which we view these is influenced by the built-in functions that we have access to in the calculator. And so this is a bit of an artificial distinction here, but from my perspective, because of the heavy reliance on the calculator, there's really two main kinds of problems, and each one is based on a particular built-in function in the calculator. And so you'll see that there are two connected with the binomial. There's the binom PDF, where PDF stands for probability density function or probability distribution function. And then there's a binom CDF, which, well, CDF means cumulative density function or cumulative distribution function. And so part of the success in this section is rooted in recognizing which function is called for, and also recognizing how other types of problems, like the ones you see at the bottom of this slide here, have to be translated so that we can deal with them using the built-in functions. Let's take a look at the calculator. Now, as you know, in these videos I'm using a variant of the TI-84, and mine happens to be running what I would describe as the idiot-proof OS, and that each of the functions that you would see like on a regular old TI-83, they have this kind of a copy and paste interface that you have to work through. But the syntax of all the commands is the same, and so I'll be careful in this video to show you each of the commands so you can see the syntax. Anyway, the two built-in functions that we were talking about can be accessed through the distributions menu. You go second, and then you hit the vars key, and it takes you to this submenu here. And if you go up, you'll notice that we have two functions, actually three. We don't really use one of them, that are connected to the binomial distribution. It would be letters A, B, and C. So letter C, I don't really make much use of in our course, but we do use A and B fairly heavily. So letter A, again, is the binom PDF, and letter B is the binom CDF. And so that's how you would find them. And in order to select one, you just have to press enter after you've selected the letter of that function. Now take a look at this. The key takeaway from this slide right here is that if you are asked to calculate the probability associated with a single value of the random variable x, you're going to be using a binom PDF. P as in Peter, as in probability, well, yeah, probability density function. So if it's a single value of x, it's a PDF. If it's more than one value of x, it's a CDF. And so as long as you understand that, then the rest of this is actually pretty straightforward. Now, we're not totally skipping over every single thing in this section in the text. For example, table 9, which you can see on the screen in front of you right here, is a very helpful resource. And if I was in your shoes, I would want to have that in my notes, because that would definitely be something I'd want to have as I go through these problems. Confusion over what the English translates to is a common point of confusion. And so this is a great thing. Now, that said, when you're looking through this example that's on the screen right now, you notice some formulas, some combination notation, and that sort of a thing. And the formulas, I mean, if you know about them, it's certainly not a bad thing. We actually skip the section where you would find this notation. So we're not really holding you accountable for this. But if you want to read it, it's in the end of the previous chapter. And if you read it, it would be a good thing. But it's not something that we require. So you don't have to worry about the formula so much. The way that they show it being calculated here is covered by the functions that we just talked about in the calculator, the binom PDF and the binom CDF. And something else that's always helpful in the text. In most of the sections of the text, they have this technology step-by-step that kind of tips you off regarding whether there's something you should know based on the calculator usage. And so here in this section, you have the technology step-by-step, which is showing you how to do a couple of different binomial probabilities using those built-in functions we just mentioned. Anyway, the rest of the stuff in the section, like for example using the binomial table, I mean, if you want to read it, that's perfectly fine, but we're not holding you accountable for table use. And in fact, when people talk to me about this, I always discourage the use of the tables. I much prefer using the calculator. So let's take a look at an example here. You can see the example that I've chosen right on the screen in front of you here. It's number 37, and it's titled Toilet Flushing, and it says, in the Healthy Hand Washing Survey conducted by the Bradley Corporation, it was found that 64% of adult Americans operate the flusher of toilets in public restrooms with their feet. Suppose a random sample of n equals 20 adult Americans is obtained, and the number x who flush public toilets with their foot is recorded. Okay, so there are several parts here, and we want to address each of these in turn. Part A is asking, why is this a binomial experiment? Well, let's take a look. So if you recall, and this is covered in the previous video if you haven't watched it, but this is a binomial because we have 20 trials. So in other words, we have a fixed number of trials. They're independent. How do we know this? Well, again, read the problem. It says here that we have a random sample, and so that tells us that there is no connection between the subjects, and so definitely we have independence. And we also have a binary outcome because it says they either flush the, well, I mean, it can be understood that they either flush the toilet with their foot or they don't. And the probability of success is fixed because we're defining success here as flushing with the foot. And it clearly states that 64% of adult Americans operate the flusher with their foot. So that would be your fixed probability of success right there. So all four of those conditions are satisfied, and that tells us that we can use a binomial model. And that's basically what I said. Now, I also will typically jot down a few other things as I go through here. For example, the number of trials and the probability of success. And I'm using P to denote the probability of success here. That's fairly standard notation, and you'll see that replicated in the examples if you read them. So anyway, let's do, that's our answer to part A right there. Why is it a binomial? It's again because we've satisfied the four conditions. And so let's look at the next part. Part B says, find and interpret the probability that exactly 12 flush public toilets with their foot. Okay, so I'm going to write something, and let's take a look. You'll notice that I wrote here the probability that x is equal to 12. And that may not seem like it's real significant, but what I find when I'm looking over people's work is that the commonly understood advice that you shouldn't sweat the small stuff is exactly wrong here. Because the people who are sweating the small stuff are also going to get the big stuff right. And so using the appropriate probability notation is part of sweating the small stuff, if you will. If you wanted to make some kind of an analogy to explain why the proper use of the probability notation is so important, think about writing an essay for a class, like a paragraph or an essay. And let's say you decided, for example, that you didn't need to bother with the verbs, or you didn't need to bother with some of the other key parts that you would typically expect to see in an essay. How do you think that would go over with the instructor of that class? I don't know for a fact. I mean, I'm just speculating here. This is purely hypothetical, but I'm thinking that that would not go over very well. It would be like a lead balloon. So it's the same here. And when you skip over that probability notation, what I see very often is that people who say that they know what they're looking for, when you look for details, you realize that they don't actually know what they're looking for. And so this is a good thing to write down. So this is a PDF, if you recall, because we're being asked to find a particular value of x, in this case 12. And so we're going to use the binom PDF function, and the syntax looks like this. So it's binom PDF, and if you look at the various parts there, the 20 is the number of trials, the middle number 0.64 is the probability of success, and the last number 12, that's the number of successes we're looking for. Let's get this from the calculator. So here's my calculator. Now I've already got the function I need selected, so let's just enter. And again, it's 20 trials. Probability of success would be 0.64. And the number of successes I'm looking for would be 12. And so if I paste that in, you'll see the syntax of the command. There you go. And to get the value, just press enter. And typically, if you're recording this type of a probability, unless it's unusually small or unusually large, 4 places is generally sufficient. And so that's what I'm going to record here. And so there's my answer. And that's a reasonable model for what I would be looking for on an exam. You know, if you're answering an open-ended question that involves a binomial, we're not asking you to write tons of stuff. What you see there for part B is perfectly sufficient, but it is the bare minimum. And so if you want to write more than that, I'm probably not going to complain. But if you're going to write less than that, that could be a problem. I've had people write all kinds of stuff in response to this. And so I'm making it clear that what you see right there is the bare minimum for part B. That's what we'd want to see. Part C says, find and interpret the probability that at least 16 flush public toilets with their foot. Now this is one of those instances where that table could come in real handy. Take a look. Here's table 9 again, and you'll notice that at least can also be expressed in other ways, but it translates to greater than or equal to. And so if I was writing some kind of a probability expression, here's what I need. Again, part C says, find and interpret the probability that at least 16. So there's my probability notation. And again, that's a very important thing to have down, because when I see that someone has the correct expression, that communicates very clearly that they know what they're looking for. Now think about this. Notice that what I just wrote is not conforming to either of the first 2 cases that we discussed. It's not probability of x equal to x, nor is it the probability that x is less than or equal to x. It's one of the last bullet items down there. It says any other kind of problem, e.g., and then it gives you some examples. And so this is one that has to be done indirectly, because it's actually going to make use of a complement. And so maybe that's something we should talk about as well. I find that people get very confused about complements, and that confusion manifests itself here when you're dealing with the binomial. So as a very brief aside, take a look at this example. I have a sample space associated with tossing 3 coins there, and I've set aside an event, E, which represents 2 tails. And notice I have it in red to make it easier to see. Now the complement of that event is everything in the sample space which is not in E. So in other words, it's all of the white elements from the sample space. And you can see down below that the complement of E contains 5 elements. And so in English, we would just say very glibly, that's not E, or not 2 tails. But having a clear understanding of what the complement is vital here, because if you don't, then it's very hard to get the probability correct. So let's go back to our writing, and we'll showcase that. Now, we're going to use the complement rule here. And so if you need to review that, you can go back and look at it in the previous chapter. But what I'm saying in effect is that the probability that x is greater than or equal to 16 is equal to 1 minus the probability of the complement. And the complement of greater than or equal to 16 would be less than 16. And because this is a discrete distribution, that's a very important distinction. It won't be so important later when we deal with continuous distributions, but it's very important here. And so if you understand, what does that translate to? It translates to this. Because we're dealing with a discrete distribution, we can't have a value that's between 15 and 16. It's 15 or it's 16. And so in this case, the complement, in other words, the probability that x is less than 16 is really the probability that x is less than or equal to 15. And that's a very, very important insight. So the syntax of the command that we're going to enter is going to be as follows. So we're going to use a CDF because it's asking for probabilities associated with more than one value of x, and we're also using a complement. And so that's why this is such a great example, because there is a lot going on here. Let's go back to the calculator and get this probability. So again, you have to go to the second VARs menu, and we're actually looking for a CDF. And I forgot to do something. I did something kind of dumb. Let me quit this here. I have to do 1 minus first, and so unfortunately you can't key that in after the fact. So it's going to be 1 minus the binomial CDF, and so now I'll put in that CDF. So it's letter B, and the inputs would be as follows. We're looking for 20 trials. Probability of success is 0.64, and we're looking for 15 or fewer successes. Here's the syntax, as you can see. And it looks almost the same, except you'll notice it's a CDF instead of a PDF. When you press enter, there's the value. And if you were to render that to 4 places, here's what you would get. So rounding that to 4 places, I would render that as 0.1011 and some change. Let's look at the next part. Now notice I've overlooked a question regarding interpret. Each of the questions that I've done so far, part B and part C, says find and interpret. And so as far as interpreting the probability, you can give some kind of a boilerplate answer. I'll make sure to give that here because I'm going to answer part D. So it says find and interpret the probability that between 9 and 11 inclusive flush public toilets with their foot. Okay, so let's go and write down what we need to do. That English phrase, between 9 and 11 inclusive, is translated as you see on the screen here. It means 9 is less than or equal to x, and x is less than or equal to 11. Now, if they don't include inclusive at the end of the phrase like that, then it means it would be a strict inequality. But because they said between 9 and 11 inclusive, it means the endpoints are in. And so it has to be less than or equal to for your inequality symbols. Anyway, this one is actually going to require 2 separate binomial CDF expressions to obtain, because if you notice what we're doing here, it's as follows. So in other words, we're calculating the probability of x being equal to 9, 10, and 11. And we could do it directly if you wanted to, using 3 separate binomial PDFs, but it's easier to do it this way. And so we're going to use 2 separate binomial CDFs. And notice how I changed it at the end right there. It's x less than or equal to 11 minus x less than 9, because we want to include the probability associated with 9 in our answer. And so if I was using less than or equal to 9, then I would be excluding it. And so I'm making it less than 9 to include it. And so if you think again, what does that mean in terms of a binomial, which is a discrete distribution? Well, it means this. And the reason for that is because less than 9 with a discrete distribution means less than or equal to 8. And so it's two separate CDFs. So as you can see, and the easiest way is just to key them both in at one time and let the calculator do the calculating. So first, the binomial CDF for x less than or equal to 11. And we're going to subtract from that the probability that x is less than or equal to 8. And so you can see the tail end of the first command at the left end of the screen there. And then the right side of this is the probability that x is less than or equal to 8. And the value is, as you see, and I would render that as 0.2436 to 4 places. So let me jot that down. So I've included my interpretation here, as you can see, and a good boilerplate answer that would cover all of the previous parts with a little bit of adjustment would be as follows. We're saying, look, if we repeatedly took samples of 20 adult Americans, we would find that on the average, somewhere around 24% between 9 and 11 of those people in the sample would flush public toilets using their feet. So there's a little bit of law of large numbers here, and it is an average rate. So that's why we're including the phrase on the average. Anyway, let's look at the next part. Part E says, would it be unusual to find more than 17 who flush public toilets with their foot? Why? So a two-part question there. Let's see what we would say in response. Now first, remember that when Sullivan asks whether something is unusual or unlikely, he's really asking, is the probability associated with that less than 0.05? In other words, less than 1 in 20. And so really that's what he's asking here. He wants you to calculate the probability of more than 17, and then if it's less than 5, we would respond and say it's unusual. So let's write that down. So the probability that x is more than 17 translates to x greater than 17. And again, that is a right-tailed region, if you will. And so in order to use the built-in functions that we have to make use of a complement. So the complement of x being more than 17 would be that x is less than or equal to 17. And so we're using the complement rule here, and we're taking 1 minus the probability of the complement. And so as you can see, that translates to calculator syntax of 1 minus the binomial CDF of 17 or less. So let's get that probability for you. So don't forget the 1 first, 1 minus, and then the CDF. And again, it is 17 or less. Everything else is already in place. There's your syntax, and there's your value. And if I was rendering that to 4 places, I would go with 0.0096. And that's a fairly small probability, but still, I'll just truncate it there like that. Let's jot that down. So with regard to our comparison, you'll notice that 0.0096 is less than 0.05. And since it is, we would say that yes, this is unusual, finding that many. Hope that's been helpful. And if you have any questions about this, feel free to drop me a line. Otherwise, take a look at the next example we have in the next video.